Now, let's look at a definition which we will use in the following theorem. For each positive integer n where n is greater than or equal to 2, we define the so-called identity matrix, denoted by I subscript n, as the n by n matrix whose entries are 1 on the main diagonal and 0 otherwise. For example, I2 is the matrix 1 0 0 1, I3 is the matrix 1 0 0 0 1 0 0 0 1, and I4 is the matrix 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Note that the ij entry of In is 1 if I equals j, and 0 if I is not equal to j. Now we go to the theorem. Let A, B, and C be matrices of appropriate sizes so that matrix products are defined. Then, A times I equals A, and I times A equals A, where I is the identity matrix we've just defined. Secondly, A times bracket B times C equals bracket A times B times C. In other words, matrix multiplication is associative, so we are free to choose which two matrices that we multiply first. For the third point, A times bracket B plus C equals A times B plus A times C. The fourth point, bracket A plus B times C equals A times C plus B times C. The third and the fourth points show that matrix multiplication is distributive. The fifth point, lambda times bracket A times B equals bracket lambda times A times B equals A times bracket lambda times B, where lambda is any real number. This means that in matrix multiplication, we are free to move the positions of the scalars in between the matrices. The sixth point, the transpose of A times B equals B transpose times A transpose. As before, we write B equals B1, B2 up to Bk, and C equals C1, C2 up to Ck, be expressed in terms of their columns. For the first point, we'll let Ai denote the ith row of A, which has entries Aij, and Ej denote the jth column of I. Note that Ej has 1 in the jth position and 0 elsewhere. Then the Ij entry of A times I is Ai dot Ej, which equals Ai1 times 0 plus Ai2 times 0, and so on, plus Aij times 1, plus all the way to Ain times 0. So this equals Aij. So A times I equals A. Similarly, we can show that I times A equals A. For the second point, A times bracket B times C equals A times the matrix with columns B times C1, B times C2, up to B times Ck, using the second point of the first lemma. Using the same result again, this equals the matrix with columns A times bracket B times C1, A times bracket B times C2, up to A times bracket B times Ck. Using the third lemma, this equals the matrix with columns bracket A times B times C1, bracket A times B times C2, up to bracket A times B times Ck. Using the second point of the first lemma, this equals bracket A times B times C. For the third point, A times bracket B plus C equals A times the matrix with columns B1 plus C1, B2 plus C2, up to Bk plus Ck. Using the second point of the first lemma, this is the matrix with columns A times bracket B1 plus C1, A times bracket B2 plus C2, up to A times bracket Bk plus Ck. Using the first point of the second lemma, this equals the matrix with columns A times B1 plus A times C1, A times B2 plus A times C2, up to A times Bk plus A times Ck. We can break this off into the sum of two matrices. One has columns A times B1, A times B2, up to A times Bk. The other matrix has columns A times C1, A times C2, up to A times Ck. Using the second point of the first lemma, this equals A times B plus A times C. For the fourth point, bracket A plus B times C equals the matrix with columns bracket A plus B times C1, bracket A plus B times C2, up to bracket A plus B times CK, using the second point of the first lemma. Now, we use the third point of the second lemma to write this as the matrix with columns A times C1 plus B times C1, A times C2 plus B times C2, up to A times CK plus B times CK. We write this as the sum of two matrices. One has columns A times C1, A times C2, up to A times CK. The other has columns B times C1, B times C2, up to B times CK. Using the second point of the first lemma, this equals A times C plus B times C. For the fifth point, lambda times bracket A times B equals lambda times the matrix with columns A times B1, A times B2, up to A times BK, using the second point of the first lemma. By definition of scalar multiplication, this equals the matrix with columns lambda times bracket A times B1, lambda times bracket A times B2, up to lambda times bracket A times BK. Using the second point of the second lemma, this equals the matrix with columns bracket lambda times A times B1, bracket lambda times A times B2, up to bracket lambda times A times BK. Using the second point of the first lemma, this equals bracket lambda times A times B. The third expression is A times bracket lambda times B, which equals A times the matrix with columns lambda times B1, lambda times B2, up to lambda times BK. By the second point of the first lemma, this equals the matrix with columns A times bracket lambda times B1, A times bracket lambda times B2, up to A times bracket lambda times BK. Using the second point of the second lemma, this equals the matrix with columns bracket lambda times A times B1, bracket lambda times A times B2, up to bracket lambda times A times BK. Using the second point of the first lemma, this equals bracket lambda times A times B. For the sixth point, let A have entries Aij and B have entries Bij. We also write A transpose to have entries alpha ij and B transpose have entries beta ij. We know that alpha ij equals Aji and beta ij equals Bji. Now, the ij entry of B transpose times A transpose equals row I of B transpose dot column j of A transpose, which equals beta I1, beta I2 up to beta Ik dot alpha 1j, alpha 2j up to alpha kj. This dot product equals beta I1 times alpha 1j plus beta I2 times alpha 2j plus all the way to beta Ik times alpha kj. We can change the alphas and betas back to a's and b's to get b1i times aj1 plus b2i times aj2 plus all the way to bki times ajk. Swapping the a's and the b's, we get aj1 times b1i plus aj2 times b2i plus all the way to ajk times bki. Note that this is the ji entry of A times B, so it is equal to the ij entry of the transpose of A times B. Hence, the transpose of A times B equals B transpose times A transpose. So the proof is complete.